right, so we'll start recording now. We'll start talking about actual lecture. All right, so can everybody still see the Blackboard just fine? It's apparently in HD now. Okay, I'll assume that's a yes. Yes, okay. There's one yes. Okay, so last time we had wrapped up by basically rehashing some of the results of the paramagnet that we had derived in what, what was that? Chapter 3, I think? Yeah, when we first started talking about the relationship between entropy and energy. And we showed that using the formalism Boltzmann factors and all that we could rederive all of those results a lot more easily. Today, what we're going to start off with is using our newfound machinery of Boltzmann factors and partition functions in order to talk about the rotational states for a diatomic molecule. So rotation. Okay, so that's the heading of this section. So ultimately what we're going to end up showing is that we can recalculate the average energy of a diatomic molecule. What do we think it should be from our previous results? Do we have any expectations for what we should find? Anybody? So if we're looking for, we're ultimately going to solve for what E bar is. Do we have any notion of what that should be for a single particle that's diatomic, a single molecule that's diatomic? What have we been saying? You guys know this. I know you do. Everyone's just waiting for somebody else to say something. What's this? I omega squared. Okay, you're thinking in the right direction, Jerry. But yeah, so George got it. So the equipartition theorem is what we had been using for systems that have like quadratic degrees of freedom, and we always said that in general that we can always just write it very simply. We don't need to know like the angular momentum or the angular speed or anything like that. We just need to know the number of degrees of freedom. It'll be that over 2 times k times the temperature of the system that we're talking about, right? So if we've got a diatomic molecule, how many degrees of freedom are there? If it's just diatomic, we're not considering any kind of kinetic energies. So yeah, I mean, usually when we were talking about diatomic ideal gases, we considered their motion moving around and their rotations as well. But here, if you're only considering its rotation, then it's just going to get, what was it, like 2, I think. So forget about that for the moment. We'll recalculate it. Okay, so everyone here, I imagine, has probably taken quantum mechanics. What does quantum mechanics tell us about the energy states for rotation? Does anybody know off the top of their head? Oh, some people haven't. Okay, that's okay. If you haven't taken it, well, here's a little bit of a sneak peek. So if J labels the different angular momentum states, then the energy of an angular momentum state is just given by J plus 1 times epsilon, where epsilon is just going to be proportional to 1 over the moment of inertia. And so J is just equal to 0, 1, 2, on and on and on. Well, are all these states like specifically determined, or is there some kind of degeneracy for each angular momentum state? There's a degeneracy, right? Because if you're given a single J, then what do you have? You have all these magnetic quantum numbers, right? So they can range over some specific values. So basically, what we can either recall or assume from quantum mechanics is that for each J we have, we're going to have actually 2J plus 1 degeneracy for that state. So there are 2J plus 1 states that correspond to every single J state. Okay, so what we want to start doing is we want to write down the partition function for rotations, for these rotational states of the diatomic molecule. And so how do we do that again? Well, we just sum up all of the Boltzmann factors. So naively, we would just write e to the minus e of j all over kt, as everybody correctly recounted for the quiz today. But since there's this degeneracy in these angular momentum states, we have to include the degeneracy factor here, because there is actually multiple of these Boltzmann factors for every single j. So you include this 2j plus 1 right here to account for that. Okay, so this is the degeneracy, and this is the Boltzmann factor. Okay, let's write that out a little bit further. Epsilon k times t. Alrighty. So now, at least for the time being in this chapter, we're going to consider the so-called high energy regime. And so basically what we're going to assume is that this quantity right here, and I'll just pick it off. So we're going to assume that kt over epsilon is going to be much, much greater than 1. So basically the energy due to the temperature versus the actual energy of the molecule is going to be, this guy's going to be much, much bigger. So this ratio is going to be much, much greater than 1. So this is the so-called high temperature assumption. And so when we start talking about quantum mechanics, we'll talk about the low temperature regime as well. That's where that'll be coming more into play when you're talking about stuff that's piled on top of each other. So more to come on that. Okay, so if we do have that this quantity right here is much, much greater than 1, then inversely, we have that this little piece right here is going to be much, much, much less than 1, right? So every single j in here is going to be very, very closely spaced. So if we take this assumption, we can assume, or we can approximate this summation here, this discrete sum over the j's, as a continuous sum, so we can integrate it. So taking the assumption we have here of the high temperature regime, we can rewrite the partition function for rotations as the following. Kt dj. Okay. Now, how are we going to actually integrate this? Does anybody have any ideas? So we want to integrate with respect to j. Is there any way we could get this into a simpler form? Thoughts? Everybody's well versed in calculus, I assume. What does this scream? Maybe it doesn't scream anything. Maybe this is a mystery. Yeah, exactly. U substitution. Nothing too complicated. So a good guess is that, well, we know how to integrate exponentials, right? So maybe we can just set x equal to all this junk in here, and then hopefully everything will work out properly down here in the factor, and we'll be able to integrate just an exponential. So let's just give it a shot. So take some x and just define it to be the quantity j times j plus 1 times epsilon over k times t. Well, then dx is just going to be, let's work it all out. So if it hits this first one, this first j, it'll just be dj times j plus 1 epsilon over k times t. And if it hits the second one inside of here, it'll be j times dj times epsilon over k times t. And what do you know? This works out to our liking. We get 2j plus 1 times epsilon over k times t dj. Well, that's great, because this is basically exactly the term that we see appearing right here. So I'm running out of space on this page, so continue down the next page. So if we use that substitution, we can say the following. Again, the limits of integration don't change. We're not changing anything there. So we'll get this factor of kt over epsilon, because we just had the 2j plus 1 over here, so multiply by kt over epsilon to get dj times 2j plus 1 in terms of dx. So if we throw that in, we get e to the minus x dx. This is just a constant, so pull it out. What is this? What's the integral of a decaying exponential from 0 to infinity? Anybody? So basically, you know the integral of an exponential, right? It's just itself. If it's negative, I see a minus from Carter. So basically, it's just 1. Because if you integrate this, you pull down a minus sign out in front, so it's minus e to the minus x, evaluated from 0 to infinity. And so doing the usual final minus initial, you just get a factor of 1. So this just turns into kt over epsilon, or in terms of our new notation, it's just 1 over beta times epsilon. Okay, so as we already seen before when we were thinking about partition functions, the partition function scales with the temperature. Which is good, because we want overall our probability to be normalized. Okay, now we're going to actually take a result that you're going to show for homework, which is the following. It's just that you can express the average energy, generally, not specifically for rotations, but you can express it generally as 1 over z del beta. Yeah. Question, Carter. Mm-hmm. Yeah, it does simplify it to e to the minus x evaluated from 0 to infinity. And when you evaluate minus e to the minus x from 0 to infinity, it's just a factor of 1. So I guess I should put a factor of 1 there. Does that help? No, our bounds don't change at all. Nope, bounds don't change. So j going from 0 to infinity is the same as x going from 0 to infinity. So no funny business going on there. But that is a good question, because you do always want to be careful that your limits aren't changing. But here we're not adding any offset or anything like that to our initial limits, or flipping them. So we're all good. So yeah, what we're going to do now is we're going to use a result that you're going to show in the homework, which is that the average energy for a system can be expressed as this combination of a derivative on the partition function and just 1 over the partition function. And you can actually probably see this pretty easily, because we know that the average energy for a system is just going to be basically the sum of E of S times P of S over all the states, right? And so basically taking the derivative here just pulls down an E of S, and the Z right here already includes the P of S that you need. So this all works out pretty cleanly. But you'll show that explicitly for homework. So if we use this result, which you will prove, it's not a lengthy proof by any means, we get the following. So we'll have del beta, because this beta epsilon is just a constant, times 1 over beta epsilon. And if we take the derivative of this guy, well, what does that turn into? So it's 1 over beta, so you get a minus sign out in front and a beta squared. One of the betas will cancel out with that beta. So you just get 1 over beta, which is equal to k times t. Okay? So basically, we've shown the exact same thing that we would have expected using the equipotential result if f is equal to 2 when we're only considering rotational degrees of freedom. So this is the same thing as we had before, where we had like u of a system is equal to n times f over 2, k times t. And if you're considering only rotational degrees of freedom, then f is 2. So u is equal to n times k times t. And so this is just the average energy for a single particle. So if you have n of them, you just throw an n on here, and you would also get this result. Cool. So we can use all the machinery of partition functions and Boltzmann factors in order to get the exact same thing that we had before for the equipartition theorem. Okay. Has anybody potentially read the text and know what kind of assumption we threw in here that was implicit from the start? That's kind of an ambiguous question, but if you've read the chapter and remember it well, you'll probably remember. Is there any overcounting that we could have done? Basic overcounting of the degenerate states. Anybody have any thoughts about that? Maybe not. So basically, through this whole derivation of the energy of the system, the average energy, we assumed when we put in the degeneracy factor that we could distinguish, basically, if we're considering a diatomic molecule, we were saying that we could consider, or we could distinguish, basically, a rotation of 180 degrees from a rotation of 360 degrees. Because when we're saying that they're implicitly distinguishable, we're saying that basically you can tell the difference between this side of the molecule and this side of the molecule. So rotating it by 180 degrees is different. So that's only true if they're distinguishable. So the result here we showed is only true if the particles themselves are distinguishable. If they're indistinguishable, then you no longer can tell. It just looks like this. So you rotate it, boom. So basically you overcount by a factor of 2, because when you rotate it by 180 degrees, you get basically the same looking thing. So you just have to divide that degeneracy factor at the beginning by a factor of 2, and you would get the correct result. So basically we'll have that this rotational average energy is going to be K times T if they are distinguishable, and it'll be just itself divided by 2 if they are indistinguishable. So just dividing by a factor of 2 because we have half the number of rotational states that we had initially thought if they're indistinguishable particles. Oh boy. Okay, so at long last, we've been using the equipartition theorem for the majority of this class, and we had just kind of said, okay, here it is. It only applies to quadratic degrees of freedom, and that's that. Just suck it up, learn it, remember it, apply it all over the place. Now we're going to get the satisfaction of finally actually proving the equipartition theorem. Okay, so is anybody excited for that? I know I was excited to see this the first time I had ever seen it. So it's always annoying when you're just told, okay, this is just a result that you need to know. It's always a lot more satisfying when you actually get to show it yourself. Sanity restored. Not a fan of proofs. Okay, hold up. This is not a proof in like a really rigorous way. We're not doing like real analysis or anything here. We're not going to be like, oh, as epsilon goes to 0, there is a bound on delta such that there is this interval, blah, blah, blah. No, it's not going to be like that. This is going to be a physics proof. Okay, so, okay, let's assume that we have a system like we've been talking about. So we've got a system with quadratic types of energy, and we'll see why this is relevant. So don't get scared of this derivation. It's not a real proof. So we'll say that the energy of the system, of the particle, looks something like this. Okay, so we've just got some dimensionful constant. I should write that out completely. Dimensionful constant. Basically, this constant is going to depend on whatever this Q is. And this Q is going to be anything like a coordinate or momentum. Okay, and then the constant right here will have dimensions accordingly to whatever that is. So generally, this is just what we mean by a quadratic form of energy. Okay? Oh, let's see. Okay, so we can write our partition function, z. As always, that's just going to be summing up all of the different energy states for the Boltzmann factor. So let's put that in. Minus beta CQ squared. Oh, what are we doing here? Ah, right. Just a second. Oh, okay. So yeah, right. So basically, at this point in time, we're talking about like classical mechanics, effectively. Like we haven't said anything's quantized about this energy. So we're gonna do something a little bit funny, and we're going to say that we can break up this Q into discrete energies, discrete energy levels. So we're gonna say that we can break it up into units of like delta Q. Know that in reality, obviously, like everything is quantized, so this is possible. So what we're going to do is we're going to rewrite this partition function. We're going to basically multiply by a factor of 1, and we're going to call this delta Q basically just the difference between different energy states, okay? So it's some small number because we're talking about large systems that are quantum systems, but we haven't really talked about in what way this is quantum. So in actuality, we're talking about a classical system, and we're just treating it as quantum. But the same results hold if we were to do this in depth and talk about it being quantum. So this is what I mean when I say it's a physics proof. So we wave our hands every now and then. But this is at least something that is fairly believable. So we can just consider breaking up the energy states into very, very small increments, delta Q. So let's do that. So if we do that, we multiply by 1 over delta Q out here, multiply by delta Q in here, so we just multiplied by a factor of 1. Nothing illegal about that. And now, since we're treating the states to be very, very close together, we treat this delta Q as being infinitesimal, and so we'll treat it as delta Q out here, although it's really a differential out here as well. And then we'll integrate basically over all possibilities, e to the minus beta dq squared dq. So we just turned this delta Q into a dq because we're assuming them to be very, very close together. Okay, so now the problem of actually writing the partition function becomes the problem of integrating a Gaussian function. And hopefully everybody recognizes this as a Gaussian. So it's something that looks like e to the constant times quantity squared, where you're integrating with respect to that quantity. Does anybody off the top of their head know what this quantity is? Do they know how to integrate this? We're going to go through it, but does anybody know the answer? Error function. Could you elaborate on that, Saif? I assume what you're saying is error function, but... Anybody else have any thoughts about this? Well, here, we'll just do it. Some square root pi stuff, maybe. Yeah, Deb's right. She's read ahead. But yeah, I mean, if we weren't integrating from like minus infinity to plus infinity, then this function has a specific name, which I think is what Saif is talking about. But here we're doing the integral from minus infinity to plus infinity, so this will have a definite value, and it'll turn out to be square root of pi, which might seem kind of odd because like where the heck is pi coming from here? But let's work it out. So let's just do this in general without these specific constants sitting out in front. We'll just focus on how to evaluate this integral. Okay, so let's say that we'll just call the integral I, and it looks like the following, which is what we have effectively. We want to integrate it. Well, what some clever people figured out is that you can square this integral. So what you'll have is basically just one integral from plus infinity to plus infinity of e to the minus x squared dx times another one over some other variable. Doesn't matter. These are all dummy variables, of course. And so since this one doesn't depend on x and this one doesn't depend on y, we can just merge them together. So we can write the double integral minus infinity to plus infinity, integral minus infinity to plus infinity of e to the minus x squared times e to the minus y squared, dx dy. Okay? So this right here can just be written as, not x, e to the minus x squared plus y squared. And at this point, there's a nice, clever little substitution that you can do. Does anybody have any thoughts about, in 2 dimensions, a nice change of variables that you could use for x and y when you have a term that looks like this? What does x squared plus y squared tell you? What is it giving you geometrically? Z squared. What is z? Okay, yeah. Huh? Yes, polar coordinates. It's a radius, right? This is r squared. Yeah, so the trick is to transform to polar coordinates. So say that x squared plus y squared equals r squared. So was my writing just before like completely illegible for everybody in terms of the sharing? That's bothering me so much. Okay, it wasn't bad. It was fuzzy, readable, but blurry-ish. Jesus, I'm so sorry. That's like, getting to the end of a race and somehow realizing that you're on the wrong track. Like, damn. I'm sorry. You guys had to live through this. These are the joys of virtual teaching. Okay, so sorry about that. That's just a thought that keeps coming up in my head right now. Okay, so we were evaluating this integral squared. And so if we transform to polar coordinates, now we're going to integrate from 0 to r, where 0 to r, or sorry, we're going to integrate over r, where r is going to go from 0 to infinity now, because r is the radial coordinate. And we'll have to integrate over our azimuthal coordinate. So I basically watched the recording to go over it again. Oh, God. So sorry. God. Ugh. You guys are going to give me some real bad reviews for that, I'm sure. I'm expecting that. Do it. Let me have it. So yeah, if we transform to polar coordinates, that exponential, it just becomes minus e to the minus r squared. I think Zoom compresses the video differently. Comes from screen share versus OBS. Yeah, that's got to be the case, Hollis. And I'm not really sure why that is. Yeah. I don't know. I'll have to figure that out later. Because it's kind of annoying using all of Zoom's built-in stuff, but whatever, if it looks better. So, okay, off on a tangent there. So we're taking this integral right here. We're transforming to polar coordinates such that x squared plus y squared is equal to r squared. So this term right here just becomes e to the minus r squared. And then our measure, the dx dy differentials, what does that become for polar coordinates? Anybody? What's the... Yes. Well, I'll use d phi, but yeah, whatever you call this coordinate. I think typically mathematicians will call this theta, whereas physicists usually call it phi. So I'm a physicist, so I call it phi. Doesn't matter. Okay, so this integral overall, it doesn't depend on phi, right? So we can carry out the phi integral all on its own, and we just get a factor of 2 pi, and then the integral from 0 to infinity of e to the minus r squared dr, right? or sorry, there's an r here. So what can we do at this point? So if this was just e to the minus r squared, we might be a little lost because there's no nice way to integrate that on its own. But we've got an r here because of this measure right here. Take 2 into the integral. What do you mean? You mean like take it from minus infinity to plus infinity and absorb the 2? Yeah, you're definitely along the right track. You don't technically like need to take the 2 in, but you're thinking about it correctly. Yeah, integrate by parts, exactly. Well, actually, no, not even by parts. It's just another simple U substitution. Not exactly. No, the Gaussian is literally what we're integrating. So the Gaussian is what we started off with, which is e to the minus x squared, right? So we're just basically proving that this is going to come out to square root of pi. So we're just going through the steps of how you actually show that. So what you would do at this point is you would take x equals r squared. Yeah, so it's just a u substitution. Dx equals 2r dr. And so then you can take the 2 out of there, put it over here. And then you've just got r dr there and x right there. So this becomes something rather nice. So what'll it be? It'll be 2 pi times integral from 0 to infinity of e to the minus x over 2, because we've got that factor right there, dx. Cool, so the 2's cancel out. And what is this integral right here? Integral of e to the minus x from 0 to infinity. Just talked about this, right? It's just 1. So this, at the end of the day, just becomes pi. But what we really want, we want just I. We don't want I squared. So real easy, just take the square root. I equals the square root of pi. So that is the integral which we set out to find. It's this integral. E to the minus x squared dx. Okay. So this is a nice thing to remember. This is a cool trick to pull out anytime. Magic. It's definitely not magic. I mean, it's actually a really fairly straightforward way to integrate something that looks like this. But it is kind of almost magic that it becomes square root of pi. You don't understand where the pi is coming from until you realize, oh, polar coordinates come into play here. Let's see, was there anything else I wanted to say about this? Oh, so if we wanted to, we could go back in and we could generalize this. So generally, we're not just going to have x squared here. We might have like e to the ax squared, some coefficient. And all that does is it just modifies this result a little bit. It'll just be 1/2 square root of pi over a. So you basically just get an extra factor of 1/2 square root a from this factor of a right here. And you could go back through and show that very, very easily. We just didn't put in for fun right here. This is also for a greater than 0. If it's less than 0, then obviously this is a totally different integral. You can't do it the same way. Okay, so that's that. That's how you integrate the Gaussian from minus infinity to infinity. Another result we're going to make use of from time to time is going to be the following. It'll be the fact that if we have an expression that looks like this and we want to take dA on it, e to the minus ax squared dx, this is going to come up just so you're aware. So I'll just show you how it works out. We would get minus x squared e to the minus ax squared dx. But we know how to integrate this. So this is just d over dA, 1/2 square root of pi over a, just using the result that I showed before. And so that, at the end of the day, is just equal to pi over 2 times minus 1/2 a to the minus 3/2. And so basically this is a nice way of showing what the integral of x squared e to the minus ax squared dx is, and it is just 1/4 square root of pi over a cubed. Not super important, but we're going to use this result in the future. Okay, so both of these results are in the back of the book as well, in like Appendix B or something. So if you didn't totally follow along, or if you want to go see it again, they're all back there and they're detailed really nicely. So now getting back to the equipetition theorem, which is what we were initially talking about, right? So we had the partition function we were trying to evaluate. So we took this aside and how to actually calculate this integral. Well, now if we go back and we use these results, then what do we get? Well, we get that z is equal to 1 over delta q, 1 over square root of beta c, where c is just the coefficient appearing in the exponential, that dimensionful constant that appears in the quadratic energy. So we can transform the integral into this, and we know how to integrate this now. It is just going to be 1 over delta q, square root of beta all over, or sorry, square root of pi over beta c. And we will just define this to be a new constant c times beta to the minus 1/2. Okay, so we got the partition function, cool. Now what do we want to do? Well, we want to take the formula that I had listed before for the average energy, and I had said it was this, and again, you'll show this, so don't worry. Okay, so let's do that. So we have minus beta to the 1/2 over c, del over del beta of c beta to the minus 1/2. And so taking the partial derivative of that, we would just get minus beta to the 1/2 all over c times minus 1/2 beta to the minus 3/2. So the c's cancel out. B to the 1/2 cancels out to the b to the minus 1/2 over here. And we just have 1/2 beta to the minus 1 equals 1/2 k times t. Look at that. So we have shown the equipetition theorem at this point. So we've said that for every single quadratic degree of freedom, that you get a contribution to the average energy of 1/2 k times t. Isn't that awesome? So basically, at this point, if you have several different types of quadratic degrees of freedom, you would just take each of these e bars, add them all up, and you just say the same thing that we had said initially. Okay? And all we had to assume basically was that the energy levels for the system were very densely packed, so that they were near continuous, so we could integrate them up like we did. But in general, we will need to be a little bit more careful for quantum systems, so just know that. So this generally will only apply for systems where the energy levels are very, very tightly spaced, aka like a high temperature regime. Okie dokie. Is everybody cool with that? It's a pretty fun result to prove on a Wednesday. I'll just label it. All right, so that's that. We showed the equipetition theorem. It is 14 after. We've got a lot to cover, so let's go a little bit further. We'll be able to get through Maxwell distribution, maybe, maybe not. We'll start it. Okay, let's start talking about the Maxwell speed distribution. Okay, so now what we want to do is we want to apply Boltzmann factors to our understanding of the motion of molecules in an ideal gas. Okay, so from what we just showed for the equipetition theorem, we showed that if you have, for example, if we're talking about like a monatomic ideal gas, you'll have 3 kinetic degrees of freedom. So you have 1/2 kT plus 1/2 kT plus 1/2 kT for the x, y, and z energies. So this is generally just equal to what we call the average energy squared, right? And this is what we called before K bar. So it's the average translational kinetic energy if we're only considering translational degrees of freedom. So this just says that 3/2 kT is equal to 1/2 mv bar squared. Cancel out the 2's. And this allows for a definition of what we call the root mean square speed. That is just the square root of 3 kT all over m. So it's called root mean square because it's the squared speed, the mean of it, and we're taking the square root of that expression. So this is just defined as the square root of v bar squared. Okay? But this is just an average value, which we can certainly calculate, but we might be interested in finding more than just an average value. We might want to find, like, for example, like how many particles are moving at or above a certain speed. So we want to develop the mathematics in order to actually deal with that. What did I write here? Okay, so let's just look at that. So, well, in general, so what we're gonna seek to actually describe, right, is gonna be something like this. So we want basically some distribution function, we'll call it, and it's telling us how the velocities are distributed. And so if we already knew the answer, which is that we're going to describe a Maxwell-Boltzmann distribution, and it looks something like this, then we would be done. What we're going to do is we're going to show why this is the case. But basically, this is the kind of thing that we want to describe. So we want to describe a probability distribution, which tells us if we like measure between here and here for velocities, exactly how probable is a particle to lie in there versus a probability of over here or something like that. And overall, like if we integrate up this entire curve, since it's telling us a distribution of all of the velocities, it should add up to 1 because it's telling us a probability. So we can write this as we typically do for probabilities. So we can say, if we want to find like the probability of V1 all the way up to like V2, whatever those are, we could think of taking whatever this probability distribution is. We don't know what it is yet, but we could integrate between the two different velocities, say V1 here and V2 here. You would just take whatever this distribution is and integrate it up. Okay, so that's generally just how we want to think of this thing. So it's just the probability of being between V1 and V2. But now we're in the position where we need to actually figure out what this d of v is. So we know how to calculate probabilities if we have something that looks like this, but how do we actually come up with it? Well, we have all the ingredients. So let's make a nice cake at this point. Okay, what's our first ingredient? First ingredient is going to be the Boltzmann factor. Factors. And the second ingredient is going to be that we're considering three-dimensional space such that for a given speed, there's a degeneracy. So basically, since we're considering we're considering an ideal gas where you got all these particles flying around with different velocity vectors, since the thing that ends up being relevant is the speed itself and not the velocity vector, there are going to be many different velocity vectors which correspond to the same speed, right? So that's basically our second ingredient here, is the fact that we can count this degeneracy, and we will count it. Okay, so just schematically, we can write this distribution as just being basically number of v corresponding to some speed v. So I'm just putting bars around this to denote the magnitude of the vector. So this is a speed times whatever the probability is of a molecule having velocity vector v. Okay, so basically the way this breaks down is, again, we've got some degeneracy factor, and what is this going to be? Well, it's going to be a Boltzmann factor. And in this case, yeah, it would just look like e to the minus beta e of s. And so e of s for us here is just 1/2 mv squared. So this will just be minus beta times 1/2 mv squared. Okay, so we have P of molecule has velocity vector v. It's proportional to e to the minus mv squared all over 2kt. I write proportional here because remember there's a partition function that's technically embedded there. Okay, so given just this expression right here, what is going to be the most likely velocity vector? Does anybody have any thoughts about that? Just given a fixed temperature, what's going to be the most likely result for v? We probably already know this because we were talking about it during the quiz. What does this Boltzmann factor look like if we plotted it versus, if we plotted it versus v? Anybody? Do we still have people here? I think so. Anybody fall asleep? Kind of Gaussian, but left-leaning. Well, yeah. I mean, you're basically right. So what'll be the biggest value for e to the minus v squared over t, basically? So the bigger I make v, right? Since this is a decaying exponential, it'll decrease. So the most likely one would just be v is 0, right? You're on the right track thinking about VMRS is largest, but we're just considering the straight up probability that it has a velocity vector, v. What'll modify this is basically the degeneracy factor right here. So right off the bat, if we only had this term right here determining our distribution, v equals 0, right, would have the highest probability, and it would just have a probability that is basically just 1, right, if v is 0. But how this will get modified is that, of course, there's only one state corresponding to this v equals 0 state. So the degeneracy for that state is 0. For the higher energy states, they'll have higher degeneracy, so they'll be modified. But you also have this decreasing exponential factor. So this d of v, like I plotted before, will be kind of a battle between this decaying exponential and this degeneracy factor right here. Okay, so now we just want to write down exactly what this degeneracy factor looks like. So basically how you can think about this is if you've got some monatomic molecule, if you just got a particle with some velocity vector v, and I plot it on three-dimensional space of vx, vy, vz. Let's say it has a velocity vector that looks something like that. Well, the number of different v's, the number of different velocity vectors that correspond to this same speed, right? So if I were to draw the number of velocity vectors with the same speed, I would just trace out a sphere, right? This is awful. Weirdest sphere in the world, but hopefully you can picture what I'm going for here, because anything on this shell will have the same length, right? So it'll have the same speed. So basically, if we write this schematically, we have that our number of vectors v corresponding to a magnitude or a speed v, that should be proportional to basically the surface of the sphere, which will be 4 pi v squared. right? So that's just the surface area of the square of the sphere. So basically, the bigger v is, the more space there is for there to be other velocity vectors that appear on here and have the same magnitude. Okay, so it'll always be proportional to something like that. And I write proportional because there's some constant of proportionality that'll put them together. Okay, so now we can write, and I'm almost done, I promise, d of v. So our distribution function looks like 4 pi v squared, basically this degeneracy factor, so it's proportional to that. It's also proportional to this Boltzmann factor, e to the minus mv squared all over 2k times t. And now we just want to determine what the constant of proportionality is. So we want to turn this from a proportionality statement to an equality. So in order to do that, we got to put some constant here. Does anybody have thoughts about how we can determine the constant? Something I said previously should hopefully give you a hint. Normalize, yeah, Jacob's got it. So yes, we want to normalize this. What do we want to normalize it to? Should it be normalized to 100? 1, yeah, Carmen's got it. So yeah, obviously if we integrate up the probability of being in any velocity state, overall that should add up to 1, because it's got to be in some state, right? It can't just not exist. It's nonsense. So what we can do is we can say 1 is going to be equal to the integral from 0 to plus infinity, because obviously speeds are only positive, right? We don't have a such thing as a negative speed, at least not for the system of molecules like this. So we can write this as 4 pi c integral from 0 to plus infinity of v squared e to the minus mv squared all over k times t dv. All right, so I think I already showed what this comes out to be before. We can just show it again real quick. So if we let x be v times the square root of m over 2k times t, then dx is just dv times the square root of m all over 2k times t. And so we can solve for dv in terms of dx in this factor right here. And we can get the following. So 1 is just going to be equal to 4 pi c times the factor 2kt all over m. And this is all going to end up being to the 3/2. And then our integral just becomes 0 to infinity, x squared e to the minus x squared dx. And so specifically, this is the integral that I talked about before, although it's the same thing here, just with some extra factors appearing. So then if we just use the result that I listed before for this, we get the following. So it'll be 4 pi c square root of pi all over 4 times 2kt all over m 3/2. So the 4's cancel out. So yeah, this whole thing, it was just 1/4 square root of pi. That's the only terms that's contributed here. So let's condense this a little bit further. So it is c times 2 pi, just condensing this square root into this piece right here. It'll become 2 pi k times t all over m to the 3/2 should be equal to 1. So you can solve for c, and c is just going to be m all over 2 pi k times t to the 3/2. So look at that. Now we can finish this up. So we wrote the proportionality before, now we have the full statement. So we can write equality, because we've determined what c has to be. So it's going to be m all over 2 pi k times t to the 3/2 times the degeneracy factor 4 pi v squared times the Boltzmann factor e to the minus mv squared all over 2k times t. And this is precisely what we call the Maxwell distribution. And so this is just the distribution of speeds for an ideal gas that's monatomic, so it only has kinetic energy, or yeah, translational degrees of freedom. So let's see. Yeah, we can probably end right here. I think that's probably enough material. We'll talk a little bit more about what this looks like in terms of average energies, root mean square, average velocities, root mean square velocities, and maximum velocities, because it has some interesting features that are a little non-intuitive. And then we'll also talk about what? We'll talk about the relationship between partition functions and free energy. And then we will finish up with a little bit of the ideal gas law, and then we might even start chapter 7. But I'm going to guess we won't at the pace we're going. Okay, so was everybody satisfied with that? We got to see a proof of the equipartition theorem today, proof in air quotes, obviously, and we derived the Maxwell-Boltzmann distribution, Maxwell distribution, sorry. So these are all really, really deep things that come up all over the place, so hang on to them. You'll use them a lot in the future. I'll stop sharing, I guess. Does anybody have any questions? Do we have fun? Are we asleep? No? Okay, good. Okay, so yeah, I'll be posting homework for chapter 6 today. Don't expect it to be terribly long, hopefully. It's only 8 problems compared to 10, and I feel like they're a lot easier than normal. And good luck on the exam tomorrow. So yeah, if you do have questions about the exam, feel free to hang around for office hours. And I'll have my phone and email open all day tomorrow in case you have questions. Okay? So good luck on that, and we will talk more on Friday. Thanks. Bye.